Hey there, so last video I did a showcase on the CBC mode of operation on symmetric block ciphers, and it was pretty long and not very good, I thought, but I'm going to try to redeem myself in this video and showcase the attack that I left the vulnerability in the last video for. And if you didn't watch the video or you don't care to go back and watch, or you don't remember, the vulnerability lies within this function check and strip padding, where we're actually raising a value error if we check the padding and it doesn't follow PKCS number 5 specification. This seems altruistic, and it is altruistic in the sense that it's trying to alert the user that something had happened that gave a plain text that is not looking so right. But by doing this, we end up giving more information to an attacker, which can utilize this, as we'll see in this video, to their advantage to be able to resolve the entire plain text. So, as a disclaimer, don't use any of the code that you see in the video for production systems. Don't trust it, it's not secure. Also, don't use the attack I'm going to show you maliciously. The knowledge is just for just knowledge. I don't condone any malicious attacks of any kind, so don't do it. Now, going through just real quick to show the basis of the attack in the maths. We know how CBC mode works. Encryption is pretty simple. We're just chaining our ciphertext to our plaintext. We also have an IV that we chain to the first plaintext block. And then decryption is like the reverse. We decrypt our ciphertext and then chain it to the previous ciphertext, and we do that until we resolve all of our plaintext. Now, in this implementation, which among having many other side channel vulnerabilities, we also left in a huge vulnerability with this check and strip padding function, which ultimately is what causes the block cipher, not block cipher, but the mode of operation implementation that we've created to really fail and be insecure. So just one thing to note is that when you decrypt for the next plaintext byte over, let me rephrase that. If you're decrypting the second ciphertext block using the previous one to chain to it using XOR, this previous block doesn't get adjusted by the system at all. It doesn't get decrypted, it doesn't get XORed with anything else. It's just there, and then the system will blindly XOR that block with the result of decryption over the second block over. So that's important because as an attacker, if I've intercepted plain ciphertext rather, that's the block I'm going to focus on for attacking. I'm going to modify that because I know the system isn't going to change it at all. And so any changes are going to be purely on any anything that the system will do on ciphertext, the second ciphertext block over. So that's why I picked C sub 1 in this case, in this example, to start with, to play around with. And so let's say that we did intercept some ciphertext. Well, I can modify this ciphertext and send it back to the system and then see what happens. In this case, when we just encrypt and decrypt, if we were to just change what we had as ciphertext and send it back to the system, most likely the system would give us an error back because the padding would not resolve correctly from the result of decryption. So we can use this information to our advantage. What we can do is we can say, well, I know the block I want to modify, and I know that this mode of operation likely is implemented using PKCS number 5, for instance, as a padding mechanism. So now we can use this information to our advantage and say, well, I'm going to change only the last byte of the first ciphertext block, send this back to the system along with the second block, and then decrypt until I find the byte that actually resolves to correct padding. And this will tell me that the system has resolved the last byte of that plaintext block that it gets back into a value of 1, because that's the only padding you can get while changing only one byte that would be correct. And so that's what we're doing here, is we are basically saying C1 prime is equal to the original C1 bytes up to position 15 plus our new byte that we've chosen. And then we're going to keep choosing B until we get a successful decryption. And then we can look at the math behind that and say that, well, we know that P sub 2 prime is equal to the decryption of C sub 2 XORed with C sub 1 prime, and therefore that has to be 1 if it succeeded. So we can expand on this and we can say P sub 2 prime is equal to the decryption of the encryption of P sub 2 XORed with C sub 1, and then that result is XORed with C sub 1 prime, which we have modified. Now the cool thing about symmetrical encryption is that we can just toss those encryption and decryption functions away. So now we can just simplify this into P sub 2 prime is equal to P sub 2 XORed with C sub 1 XORed with C sub 1 prime. Now, since we know P sub 2 prime is equal to 1, we just set that as the other side of the equal sign. And now we can rearrange things and we get this cool equation that says that P sub 2 is equal to C sub 1 prime XORed with C sub 1 XORed with our P sub 1 prime, which is in this case 1. So we've basically been able to take the system's altruistic notion of alerting a user to incorrect padding, and we were able to exploit that in such a way that we get enough information to calculate what P sub 2 originally was. Now, I'm not going to worry about getting the next byte for now. I'm going to just implement the first part of the attack, which is getting the last byte. So I have a plaintext, which I've chosen to be this string of letters up to O, and it's only 15 letters, which means that we're going to have a padding of 1. So we're going to encrypt it and get ciphertext, and now we're going to create a function called getLastByte. I'm going to also clear my my terminal and get that ready. Okay. I'm going to be quiet a little bit while I just set up some of the basic stuff. Okay, so here I'm just basically decoding the data since it's base 64 encoded, and I'm stealing some of my own code to split the data into 16-byte chunks now. And then now I'm going to call C prime, I'm going to make it a copy of our original C1 prime, which is just the first block. And it's all of those bytes in that block, and this is just so we can mutate something while we keep the original information somewhere. Now we do our iteration over each byte value. However, we don't just do naive iteration from 0 to 256. We're going to actually set the starting point to be the original 1 past the original byte value, so we're skipping over what the original byte value was. And then we're going to come back around and then do it last. We're going to pick the byte it already was last. And the reason we do this is just so that obviously the last byte can resolve, the original byte can resolve to correct padding if we just leave it alone. But it is possible that this byte is what is correct to use to continue going forward with the attack. So we test it last, just so we don't run into any dead ends. Now our last byte in our C prime becomes the byte. And we have a to-test vector, which is just base 64 re-encoded data, which happens to be C prime plus the original C2. And now we try to decrypt this. Decrypt it. And if it works, let's just print out the byte value, which for the last position in this case should be 1. And again, the formula is just the byte that we're testing, XORed with the expected padding, which is 1 in our case, XORed with the original ciphertext byte. And then if we get an exception because of the padding error, then we just pass. So this is the function to get the last byte, and if we run it, we will indeed get the last byte. If I could code correctly. There we go. There we go. Okay, we get the 1. Now, when I said we need to do some extra stuff to get the next byte over, what I mean is that when we're getting the next byte over, which is the second to last byte of the plaintext, we're actually going to have to find a way to resolve both that byte as well as the last byte we just got the plaintext for to be 2 when we decrypt it. So for the second to last byte, we obviously are just going to iterate over those values, but for the first one, we need to calculate another C prime value. So the way we do it is we just rearrange the equation we got to get the plaintext byte, but now the unknown becomes the C1 prime byte. So we just set that as our unknown, and now we get our new C sub 1 prime is equal to P sub 2 XORed with C sub 1 XORed with our new padded value, which is 2. Naturally, if we move 1 byte over again, the expected padding changes to 3. So each time we're going to need to recalculate the ciphertext prime bytes that we've already gotten plaintext for. So if we were to show that, then in this case, we're going to actually store the byte value rather than just print it out. So plaintext byte equals 0, and then we're going to do another iterative step, which is again an iteration from starting from the original byte value. And careful about your indexes. And then now for the last position, it's actually going to be the plaintext byte XORed with the original ciphertext in that position, XORed with our new expected padding, which in this case is 2. So again, to test, we just do the same thing as last time. We concatenate C prime with the second block of ciphertext, and then we test it, being careful again to check our indices in the equation following successful decryption. And now we can print this out. And because it's going to be O, I'm actually going to print out the character, not the byte value. So this looks good, and when we go back, we should get the O, and we do. So we can do better with this. We don't actually need to go through each time, because that'd be annoying. We'd have at the end of that like 16 of these, well 15. And it's very annoying to do that, so what we're going to do instead, we're going to vectorize everything. And what I mean is that we're going to, instead of working with individual byte values, we're going to work with byte vectors. So our plaintext byte now becomes plaintext bytes, and it's just going to be a holder for any future values, so it'll just be zeros for now. 16 zeros. Now we're going to have an outer loop that's going to iterate over all the possible byte positions, starting from the last byte position down to the first. And in this becomes our inner loop, which is going to test all the byte values for that index. And again, we need to be careful of our indexes, so our indexing becomes now 15 minus I. When I is 0, we get 15, which is the last byte. And you know how the rest goes. Likewise, we'll need to be careful about our expected padding, which now becomes I plus 1. And instead of printing, we're going to store now in the position that we need, whatever the plaintext is. Now we're going to also have a vector called expected padding, which is going to be zeros let's see, 0 for blank, and the range of 16 minus I. So when I is 0, we're going to have 16 zeros, because we don't need to XOR the padding with anything quite yet. But when we do need to, we're going to pad with the expected padding, which is I plus 1, for the range of I. So if we were padding in this example of getting the second to last byte, then this vector actually ends up being just 15 zeros with 1 2 at the end, versus what we would normally say would be the 2 2s at the end, because we don't want to XOR in the position of the byte we're changing. It doesn't really matter, but I'm very picky about making this obvious in the code, so that's the way I'm writing it. And now our C prime becomes, this is, by the way, the vector utility that I've created for XORing complete vectors, and this is all available. The source is going to be available. So this becomes the XOR of the expected padding with the plain text bytes, which is also XORed with, whoops, the original ciphertext, C sub 1. So that looks good. So now this should actually go, and actually we should break after we get our plain text byte. So this should run and aggregate all the plain text bytes, and now I'm going to print them out. Actually, I'm not going to print everything out. I'm going to get rid of the padding as well. So unless, if b is greater than 16, meaning it's not a padding byte, we print it, otherwise we leave it be. So now when we run this, we should actually get the entire sequence. Whoops. Where did I mess up? Plain text bytes. That was dumb. Alright, so after that little hiccup, we get the entire string. So that's pretty cool. Now all we need to do is just make it so that we're not working with only 2 blocks at a time, that we can get this, we can get the plain text for any number of blocks. So the way we do this is now we just change this to find bytes, just to make it a little more clear. And then we're going to instead create a function called find plaintext. So let's go ahead and make that. Now I'm going to move this stuff to this function and make this argument blocks. I'm going to have plain text, which is just going to be a string where we aggregate all the plain text that we get, and I'm going to just return the string that we joined together from that find bytes function. Now for the range of blocks that we have, which is the split blocks, again, we're going to have however many blocks we get, we go up to the last. Actually, we're going to do -1 because we don't want to do this for the last block, we don't care. But we're going to say plain text is equal, plus equals, find the bytes of blocks I to I plus 1. And at the end of this, we're going to print out the plain text, and now because here I have much more than 2 blocks, not much more, but I have more than 2 blocks, it should still work. It's just basically going to take two blocks in sequence at a time and then move forward. So out of range. I done goofed. Oh yeah, because it's not I+1, it's I+2. There we go. So now we're able to get the entire plaintext. So this is how the attack works, and I hope it was pretty cool to see this in action and see how simple it was. And again, please don't use this maliciously, but this is a cool attack. It's probably one of my favorites. But yeah, I'm going to try to put out more crypto vids, and I enjoy doing this one, and hopefully it was short enough. So, till next time.